Okay. Yeah. Yeah.
So, yeah. So today we are going to review some of the basics of photovoltaics. I believe you already have gone through some of
Yeah. Dr. Menon went through some of this stuff
yeah,
in
some
one
of
of
the
the
basics
lectures.
of photovoltaics, but just like reviewing it. And yeah, so apart from Apratim, also slight courtesy to Dennis Cruzan, Steve Blair, and Mike Scapula. If any of you is interested, Mike is doing pretty good work on photovoltaics lately, so you can look into some of his work on photovoltaics. So, yeah, so without wasting much time, let's just start off what I intend to cover or what we intend to cover in class today. So, we are going to go over 4 sections, as you can see. The first section we are going to just talk about basics or just like what is or what are photovoltaics and where are they used. In the next section, we are going to answer another important question that we have is why do you want to use photovoltaics? I mean, what's the use? In that respect, we are going to talk about the current status or the current state of the art for these photovoltaics or the field of photovoltaics in general. In the third section, we will be talking about much more technical aspects of solar cells or like how do basic solar cells work. And we are also going to talk about some of the matrices or performance matrices of the solar cells. That is, how do we measure the quality of our solar cell, as well as how do we measure the efficiency of these solar cells. Before concluding our presentation or the final section of this talk, where we are going to look about what are the different types of solar cells that are present there and what kind of engineering or what kind of different alternative technologies are there to make these kind of champion devices as as the TA prefers to call them. So basic history of these solar cells. So the concept of solar cells is nothing new. It's like dates back to roughly 250 years ago. The first guy, Henry Becquerel, was the one who came up with the idea of photoelectric effect. He proposed this idea when he was just 19 years old, back in the year 1839, and this led to a lot of people studying the photovoltaic effect and how this can be used to make useful devices. So, just 50 years forward, we have a gentleman by the name of Braun, and Braun succeeded in demonstrating the first rectifying metal lead sulfide contacts, which was later uh, developed much more by this two gentlemen here, Walter Schottky and Sir Neville Mott, who used all these concepts from like 100 years ago and formulated what we know today as the theory of metal semiconductor diodes. Again, coming back more 50 years, 100 years, the field matured more. And what we have here is two gentlemen by the name of Russell Owl and Jack Scarf at Bell Laboratories, who demonstrated for the first time doping effects in silicon and germanium as well as the pn-junction, and this was the stepping stone, or I should say the main cornerstone of the field of photovoltaics back in the year 1939. So you can read up on how the field of photovoltaics or the field of solar cells evolved from this oh yeah, so this site here, or even the Wikipedia is also a very good site to know about how this came into existence. So solar cells. So we have solar cells, and what encompasses the solar cells is the field of photovoltaics. The basic question which comes here is what is a photovoltaics? Or like mention the term photovoltaics, what do you mean by that? So let's first think of a black box structure, something like this. Let's just simply think of a black box like structure. So what is?
Sorry for the interruption. So I'm recording from the mic
Okay,
on the
okay.
laptop. So it's good if you don't walk
Okay,
to that
fine. I'll stick to this side.
Sorry.
So yeah, fine. So the thing is, so what is a solar cell? So if you think of a black box structure, very simple black box structure, what a solar cell does is it takes in the sunlight and converts it into electric current, which again can be used for different purposes. That is, it can be used for a charge controller device, a battery system if you need DC power, or even if you need an AC power, you can use it in inverters. So you can think of a solar cell as nothing but a backward LED. Now, let me ask you a simple question. What does an LED do? Anyone?
Produces light.
Okay. With what?
Converts the electrical energy to what?
Yes. So what the solar cell does is basically a reverse process of this. So with an LED, you have an electric current which produces light. With a solar cell, you take light and you produce electric current. Now, from a very technical perspective, if you think of this, this just acts as a semiconductor diode. Now, this will be clear in the subsequent lecture slides that we'll go through. But for now, with this understanding of how the field of photovoltaics or solar cell works, let's revisit some of the non-technical details first. So, when you think of the okay, I need to read this side. So when you think of the traditional fossil fuels, what they do is the fossil fuels are the main source of energy for us in a current scenario. The solar cell or the field of photovoltaics is an alternate field. So in a conventional fossil fuel based system, what you have is you generate electricity using steam turbine engines or generators in general. Now this, if we reverse back or trace back the process, we see that these kind of turbine engines work on fuels or coal, which is the cornerstone of any combustion system. Now this coal is achieved again by hundreds or millions of years of recycling or of this kind of trees or animal remains, which are under the earth for millions of years, and they get turned into coal, which is used from turbine engines to produce energy. Now the source for all these kind of plants, leaves, animals, anything is sunlight. So let's do a very simple math. So the amount of sunlight that gets transferred as energy by plants is roughly 3 to 6%. Out of this 3 to 6%, the amount of energy that we get through coal is roughly around 50%. So let's say if you take 3%, 50% of that is roughly 1 to 1.5%. Now combustion engines with an efficiency of 95% roughly hovers or gives you energy which is 0.5% of the total solar energy that we receive. Now let's look at the field of photovoltaics. So if we take this system and try to simplify this, what can we do? Can we do better? That's the question. So let's take sunlight and let's build our black box or the solar panel for an instant. Now, even if I consider, so let me take you, so even if I consider that my solar panel is capable of converting roughly 20% of the total sun's energy. Now again, I must point out that this is actually a very conservative number, and right now solar cells, at least the one in research, have been shown to be almost 50% efficient. Let's forget about 50. Let's even forget about 25%. let's consider something which is in half of half than the current state of the art technology. That is, let's say consider 20%, and even if we convert that using an AC or a DC inverter, we still end up with 17% of energy starting from sunlight. So from this perspective, it is really a very lucrative way to harness solar energy as alternative forms of energy. This is a slide which all of you have seen. Is like solar energy. It can be used for a lot of different things. So with 17% conversion rate, people have really thought, oh, why not use it? So use it on rooftops, use it for electric vehicles, use it for consumer electronics and whatnot. Speaking of uses, China is currently at the forefront of all of this. So these are the two major large-scale utility power plants that China currently has for solar energy. One is in the Tiger Desert Solar Park, which has a capability to produce up to 1500 megawatts of power. The other one, which is recently coming up, is the Dayton Solar Power Top Runner Base, again in China, which currently produces about 1000 megawatts of power, and it is estimated, I guess, by the year 2020 to be able to produce 3000 megawatts of power. So apart from China, so China is off the charts. Let's look at some of the other countries which are trying to still get into the solar market. So if you see, apart from the rest of the world, which is way up there, the US is currently just looking into moving into the solar market, as you can see, over a 10-year span from 2005 to 2015. From the latest report that was obtained from the Renewable Energy Policy Network, US had a growth of roughly close to 2% for solar power generation, where one country which really stands apart from all of this is Spain. Spain has really gone from close to zero to roughly 4%, double of what the US has in the solar market scenario. So let's, for an instance, since like we are engineers, and let's forget the environment uh, for a while, and let's see. So let's say that I'm an engineer, and yeah, I want jobs. So are there jobs in this sector? So even from this report, it's pretty clear that the current generation of jobs in the solar market is pretty high in comparison to rest of the other alternate technologies that are being developed. And honestly, like with 8.1 million jobs and more to grow, I would really consider a career in solar cells. So speaking about potential jobs and all of this of the field of photovoltaics, let's again like do some simple math. So let's consider the total flux or the total sun's energy that we receive on Earth per year is roughly around 90 terawatts. And even if we say that the global primary energy conservation is around 20 terawatts, which was estimated from this figure back in 2013 from Sandia, which stands at 17% terawatts per year. So even with around 17% of photovoltaic conversion efficiency, we hit, or let's say even if this means that we extract only 0.13%, like even less than 1% of the sunlight hitting the earth, this still translates to a lot of energy. What I mean is that in terms of square miles, let's say even if you cover the entire state of Texas, you can actually power the entire world with solar energy for 1 year. Now, this is just like nobody is going to cover the entire Texas. Like, don't be uh, so optimistic. But I guess we can. I mean, you never know. You can cover. So even if you look at this state, I guess this gives the uh, direct normal irradiance that the state that's the entire US achieves over the entire year. You can go to this web page
Yeah, this
and
was just as an example of you can find all the data in this.
so yeah, you can all find the data in this website where it really gives you what's the amount of solar irradiance at each of this state. I think this is
So if you
Texas.
no, this is Utah.
Oh, this is Utah. Okay.
You-
Yeah. Sorry.
So suppose
So-
if you go to the big map and you click on one of the states, the website gives you all the irradiance data.
Yes, so yeah, so this is the irradiance data. So this is, I guess, yeah, in 2017 it updates in real time. So even now if you go, you can probably see how much of the irradiance that Utah gets. And honestly, Utah is, if you see this plot here, Utah probably gets a lot of solar irradiance. So compared to the, yeah, compared to the eastern parts of US. So as I've shown you a few slides before, that US is actually still lacking in the solar market, but progress is still there. So the US, what it does, it launched a DOE Sunshot Initiative project back in the year 2010, I guess, where they wanted to bring down the cost of solar energy generation. So when I talk about solar energy generation, let's just think about it from a bit more practical sense. So all this while I've been saying that solar energy is great. You can have 70% with 0.13%. You can cover the entire energy deficit of this entire world. You can power this, power that. Let's think about it a bit more practical sense. So why isn't there solar cells everywhere? Why do you still have to pay the Rocky Mountain Power Energy bill every month? So there has to be something which I'm not saying, or like there has to be some problem with solar energy generation. So looking at this plot, like can any of you like guess or come up with any answers as to what's the problem with solar energy currently?
I'll say number one, the price,
Okay.
and number two, during the winter time, the snows or the dust, or it can pile up.
Okay.
Yeah, less efficiency as
I mean, the efficiency is still high. Like even if you have less than 1% with 0.13%, you can still cover the entire energy deficit for the entire year. So what I'm saying is you don't really need it to operate during the winter. So the cost is one, but what triggers this cost? Anyone?
price of the solar cell.
The price of the solar cell, right? But why? I mean, don't you think that there could be like cheaper ways to make these solar cells, or maybe we haven't done it? I mean, you are there. I mean, that's
Price
not
and
the-
efficiency of a solar cell combined.
I didn't get this point. So price and efficiency, isn't?
Yeah.
No, I didn't get this. Like,
So
I
high
mean,
price, low efficiency. That combination.
high price. So
Resource.
resources. Yeah.
Transport,
What's the export part here?
transport.
Transport. Transport of?
The solar cells from the place that they manufacture to.
I mean, you can set up the manufacturing right beside where the solar cell can be given, right? I mean, yes,
For the
you
residential, you can't do that.
correct, but you can. I mean,
And you can't set up a plant in every state.
correct. So the thing is, so let's combine all of this. Let's combine all of these thoughts. So the problem with current solar energy power generation is the cost per capita, or like the cost per unit area that we have, which is still quite high. One thing we didn't say, in comparison to the conventional fossil fuels generations that we have. So so the thing is, it's high, but it's high with respect to what? It's high with respect to the current electric uh, generation systems that we have. So if we can figure out a way of making it cheaper than your current Rocky Mountain Power energy bills, probably they'll go out of business. So what the US thought is, let's start this Sunshot project. Like, so the goals were two. So the goals were to increase this solar market, to have like really good solar cells in the market to compete with China. So, and the other one is to bring down the cost of this solar generation in three different areas: in the residential market, in the commercial market, as well as in the general utility market. So as you can see that over the years, this really has progressed as the US government wanted, and the goal by 2030. I wouldn't really say that these numbers are like accurate to the holy grail, but the projected goal for 2030 is roughly around 3 to 5 cents per watt, or for kilowatt hours. So we are still in the process of achieving this target, but that's what the current projection is. And in the next slides, we are going to discuss about what are the potential challenges, how people have overcome some of the potential challenges, and what still remains to be solved, such that solar energy, yeah.
So what is the price with the conventional method right now?
Oh, it's nearly half. Yeah. So you typically need to do a lot of advanced engineering, as I must say, to really compete with the conventional systems or the conventional electricity generation techniques. But yeah, so in the next slides we'll discuss the basics of this, how it can be achieved, and what are the problems with this. So let's start with the basics of all this, from where it starts. So it starts from the sun when we talk about solar cells. And the first thing that I would like to talk about is the solar spectrum. So if you look at the solar spectrum here, the solar spectrum ranges from 250 right up to 2500 nanometer, where as you can see that the sunlight, the spectrum of the sunlight at the top of the atmosphere is given by this blue curve, sorry, the yellow curve here. And as you can see that the spectral irradiance really shoots up in the visible range. Now, this spectrum follows the conventional blackbody radiation that you have, and as you can see that the radiation at the sea level drops, which is due to the absorption across different bands of this solar spectrum due to presence of different molecules, mainly moisture, carbon dioxide, and even oxygen. So the first primary problem starts at the source itself. That even if you look at the solar spectrum is not continuous. There are bands in between the spectrum where you have great absorption. Now, this is the first step. The second problem is to figure out a material which can really work pretty well across that huge bandwidth of 250 to 2500. Now, if you come to this plot here, you will see that there's not a single material. There's not a single material which gives you efficiency across this entire band. So there are different materials where with different band gap energies, which again absorb at different uh, regions of this entire solar spectrum. And as you can see, the efficiency is again pretty poor. So it's not weight. So we haven't yet hit across a wonder material, which, I mean, I'm not talking about graphene, but the thing is which can actually perform pretty well for these kind of solar cells. Now, speaking of materials, again materials can be, as you know, of three types. So you can employ simple metals where you have the valence and the conduction bands overlapping with each other. You can have semiconductors or you can have insulators. So the semiconductors are probably the way to go, and what I depict here are all different classes of semiconductors. So semiconductor materials seem the most viable to tackle these kind of challenges of making a solar cell. So let's say for an instance, let's think that since we don't really have a single material which can do everything, let's take one material and see what's the best we can do. Let's see. So we take a single material and try to build a solar cell. So as you can see here, there are three necessary functions to use this material and make a solar cell. The first thing is to generate carriers, charge carriers from a semiconductor and sunlight combination. The second is to separate the charge carriers from a pn-junction diode, which will be clear in a while. You still have the video, right? Or we have to pull that out? Okay. So, and the third part, or the most important part, is to collect these charge carriers to do electrical work. Carriers reach front and back on. Oh, the slide is terrible. So, so in essence, what you're basically trying to do is you're basically trying to make a cell with a front and a back contact, and you wanted to have these cascaded layers of materials to make a solar cell. So talking about PN junctions all this while, like how PN junction works. A solar cell is basically a PN junction diode. It's now let's study what a PN junction diode is. Okay. So we don't really have the video, which
it was like a cool animation.
Yeah, it's a cool animation. So let's talk about semiconductors. So one of the most widely used semiconductors, silicon. Silicon is everywhere. Now the point with this is, so silicons have what should I say, defects. Now what do I mean by a defect? So when I mean by a defect is in these kind of molecular structures. Okay, just stop me if you don't understand. So in these kind of like electronic structures of silicon, there are defects in the form of maybe not having an electron to complete the octet of my material, or whether I have an excess of one electron which in my structure. So what typically we do is in these kind of semiconductor materials, we dope it to generate these electrons, and so these gaps, since they don't have an electron, what we generate is basically a hole. And this kind of doping, what it does, it it forms a charge depletion layer. So this is actually pretty bad to understand, but still. So the thing is, when you take an N type where you have excess of an electron, and when you take a P type where you have.
So I sent you the link.
Oh, okay. Yeah, so this would be pretty
I'll
easy
do
to
it.
understand. Yeah, just the slides doesn't really tell anything. I mean, I didn't understand anything what I did. So yeah, so this is a full animation to understand. Oh, you can put that down. I don't think we need the sound.
Okay.
So yeah, so this is starting from a silicon atom, as you can see, which is a p-n junction. You can fast forward it a bit, and as you can see that impurity atoms can be added to this to increase its conductivity so that it can conduct electric current pretty good. And again, so as I was saying, there are two kinds of doping that can be done. So you can have an excess of electrons. Uh, oh yeah, you can. Or you can have an excess of holes that are missing of an electron, so as to have positive charges in your material. And since these charges are mobile or like free to move across the entire material, they can contribute to increased conductivity or increased transport of electrical current in your material. And this forms two different junctions of your solar cell, or a p-n junction diode, as we can say. So once you like sandwich both of these, so what you can have is, since these electrons just okay, so once the holes come to the electron part, they combine and you have a positive charge which is here. Once the electrons travel there, once the hole comes here, you have a essence of a negative charge, and as this process continues, you have this two charge. Yes, you have a depletion of both negative and positive charges. Just so now when you have this, when you come in and shine light on this, what really happens is you have a hole and electron pair generation at the junction. So this electric field makes the electron flow towards their respective junctions, and what you have right now is the photoelectric effect, or the photoelectric junction effect, which contributes to enhanced current across your p-n junction. This again, in conventional electric terms, creates a potential difference. And now if you come and connect a load in the form of, let's say this is an LED or an electric bulb, the charges driven around the circuit forms a conventional electric current, and what you have here is basically a solar cell, or the basic principle of how this solar cell works based on the generation of the photoelectric current. So yeah, so coming back to the slides. So no, yeah, okay. Oh. So this is what you see in the animation. So if you go back to basic semiconductor physics class, you can actually draw a band diagram for this, where this is basically, in very technical terms, has been depicted here. I'm not going to go into this, since this will go into much more semiconductor physics class, and I don't really know. Like, I know some of you have taken the semiconductor physics class, but I don't really know. But for instance, this is how the band energy diagram looks. And the next step is, if we try to visualize this effect in the form of a simple circuit that we can really make. We can actually make this is as a simple circuit where now your external load is the LED or the electric bulb. The sun basically is your photocurrent source. You have the diode, and these two basically arise from the from two different phenomena. So the shunt resistance arrives due to the defects of your semiconductor material, and the series resistance appears or occurs due to the front, and due to the front and back contacts. Now understand this properly. So the thing is, if you go and draw the equivalent circuit of this, okay, I should not go there. So if you draw the equivalent circuit of this, this is due to the defects in the material. This is due to the back and front contacts. This is the LED. This is due to the pn-junction effect due to the sun or the photocurrent source. Now let's say there are two cases for this. If we analyze that circuit, the first case is when there is nothing. So when there is no photocurrent shining on my circuit. Let's say this is not present. You just have the diode circuit. In that case, what we really have is shown by this dark curve here is what we call as a dark current. And this is technically pretty low. Let's say we come and just apply, instead of the photocurrent, we just apply a simple current across this diode. After a certain amount of voltage that is applied across the diode, you have some current which flows across your circuit. Let's say now we apply the photocurrent to the same circuit. So what it does is basically, so this is just a sign convention. What it does is right now, even with very low external bias that is applied to the circuit, we really have some current flowing across the circuit due to the photoelectric effect. Now if we translate this into a simple PV curve, we can say that the maximum power that can be generated across this voltage is something, so if that curve is translated here, that's pretty high for me to reach. So the maximum curve or the maximum power that can be achieved is somewhere in the region where you have the short circuit current and the open circuit voltage. So this is a basic, so this is a superposition of two different concepts of concept that a diode, the JV curve or the power voltage curve, is simply shifted down by the light current without changing the shape of your IV or the PV characteristics. That is, you can actually have a point where you can deliver maximum power across your circuit with a given photoelectric current generation. So once we have that circuit, let's try to analyze two cases, or like the effect of shunt. You don't have the video for that too, right? Okay. it's becoming a bit difficult. So the thing is, let's see the effect of both the shunt resistance as well as the series resistance across your circuit. So we know how the simple basic diode works. Now let's move ahead and see the effect of this shunt resistance as well as the series resistance. I'll just take the help of a plot. The formula won't really make much of sense. So what I said is that the shunt resistance occurs due to the defects in your semiconductor material. So as you can see here that let's move back here. So if we write out this equation for the solar cell, we can see that the shunt resistance term can be written in this form, where if you have a huge shunt resistance that is there, you actually can minimize the effect of this and you can have higher current across your solar cell. Whereas for the series resistance, if we forget the shunt resistance for a while and just concentrate on this term here, we will see that basically a small series resistance gives you a higher value of current there. Yeah,
So you want to add imperfections, is that right? To get the higher shunt?
you're correct. So if you see from this plots here, this typically means the same thing. It's actually difficult to make understand without the videos, but I'll try my best. So if you see that the more shunt resistance you have, you're approaching the curve that where I showed that you can have the maximum power pretty well, and that can again happen with as much of series resistance that you can have. So these two combined effects, you need to find where is the trade-off across your solar cell. Now one thing to remember here, that this again varies from material to material. So you can't really have a single cutoff point same for all the materials. It will typically vary. And based on that, you will really have to choose your series resistance or how you make the front as well as the back contacts. So this I guess this was studied, right?
Yeah.
So
But still, maybe you can go over.
okay, so I'll just go over this again. So this I believe was studied the quantum efficiency of how we define the quantum efficiency of these kind of solar cells.
Okay, so I have the video. Do you want to show them that?
Yeah, we can show.
So this
Oh
one. Right?
yes. So this is the effect of a shunt resistance, and as you can see that as the shunt resistance goes down, you typically have a problem lurking there. So when I increase the shunt resistance to a very high value, I approach what you typically would expect in an ideal solar cell, that both this curve matches. Similarly for the series resistance, oh, you have series resistance elsewhere.
Yeah, it's in one of these pages. But this is this is a
Yeah,
very
so this is
good
another
website actually.
Yeah, so this is another website that you can refer to.
So this is for
So
the
with the
series
series
resistance.
resistance, as you can see, they also have the shunt resistance there.
No, this is powered output and the cell.
Okay, so this is the power output. So as you can see, with the increase, in the series resistance, again you are starting to deviate much from the ideal scenario. But as you decrease it, you will you will slowly mimic the ideal solar cell characteristics. So yeah, you can actually go to this website, and this really has pretty cool animations. I guess to pb-education.org.
Okay.
So with this, you can really model your circuit, and based on what material you use, you can actually fix on what your series resistance is probably going to be, what kind of metal contacts that you can use, so that you have a really optimal solar cell. Now, speaking of solar cell, the next big thing is, okay, fine, I made a solar cell, but what if it's very crappy? Nobody is going to use it. So I really have to think about making a solar cell which is highly efficient. And let's say the first thing is it has a high external quantum efficiency. So this plot here that you see here in the shape of a box is what you will have in an ideal solar cell. No defect, no problem, no absorption, pretty flat spectral response, but life is unfair. Life is unfair, so such that you end up with something similar but not ideal. Now this is due to various responses. The blue response, which reduces due to the front surface recombination. So we are again going to study these effects of front surface recombination, as well as the rear surface recombination, the reduced absorption at long wavelengths and low diffusion wavelengths, which again contributes to the overall reduction in quantum efficiency, again caused by reflection, low diffusion length across my entire band. So let me stop here, and if you have any questions, I'll be happy to take it up to this time. Any questions that you have? So everyone answer everything. Uh,
It seemed like in that last photo, it seemed like it was kind of the edges that were worse. That are there like certain colors that
right.
aren't good for
Right.
absorption?
Right. So yeah. So there is. So this typically happens even if you see. I'll just go back to a few slides more. That even in this spectrum, you really typically have a lot of absorption coming in from a lot of different molecules. So depending on like what material you take and how well you engineer those materials, you typically might do a good job, but again there are a lot of trade-offs. So apart from the material trade-offs, what we are going to study next is there are a lot of structural or geometrical trade-offs in your solar cell. So problems are everywhere, ranging from geometrical defects to material defects and whatnot, which again ultimately contributes to a reduction in your quantum efficiency of these solar cells. So any more questions? Else I'll ask questions.
I have a question for you. So the reduction in cost in that one graph that you were showing
Right.
showed a drastic decrease in cost. That's due to the different materials or geometries of the solar cells primarily?
Good question. Yeah. So it's a combined effect of everything. So the thing is, the first challenge is a material. So people have been doing, as I said, like Mike Scapula. Mike has been playing around with different other materials. So as you can see, some of these materials are really pretty cheap to manufacture. Let's take, for example, graphene. You take a scotch tape, peel it off, you get graphene. Nothing can get more cheap than that. So it's the emergence of these kind of materials that contributes. Some of them are. I just took graphene as an example. Don't take it as a grain of salt. But some of these materials are mass producible, and that what contributes to a reduction in your per capita production. The second thing is again, what should I say, clever tricks in how you make these kind of solar cells. So what I typically showed you, this is So this is a very common. So this is a very common. Like you don't know anything about solar cells and you just go and make a solar cell. This is how you would make a solar cell. But this is not pretty cost effective. So people have typically found out ways on how you can actually even change the geometry of these kind of structures to make cost efficient solutions. So these are areas honestly which people are still exploring. So there's a lot that can be done here from a materials perspective, from a geometrical or a geometry of the solar cell perspective. So let's move to the next section where we are going to discuss various of these, like first coming from a material perspective and finally going into different kind of geometrical perspectives which has been covered till now to make these kind of solar cells. So let's start with the first generation or the earliest of the solar cells that we have. Was maybe start with something simple. So this was, I'm talking about this as an era even before the Sunshot grants started. So as I was saying, when the first solar cells came into being, they were simple structures as I already showed. But sometime later, people started thinking, well, we played around with materials, but after a certain point, okay, we have this kind of materials, and since the materials research is not going pretty fast or pretty rapid, let's look into engineering structures. Let's look into going into geometrical parameterization of my solar cells. So the first, so these were one of the first demonstrations from Dr. Charles Gray at Sun Power Technologies of a solar cell, which achieved efficiency of roughly close to 15%. They made it with single crystal silicon, which is 300 microns thick, and they used all the conventional back front contacts and everything. They made a solar cell of this, and this theoretically, in the absence of reflection loss, back metal light absorption, recombination losses, back surface recombination, bulk recombination, in the absence of everything, in the absence of all these losses, you could still end up with only 30% conversion efficiency with silicon. Contributing to all of this, you have roughly around 14.3% loss in your device, which brought your efficiency to something close to 15%. Now, like as engineers, we are pretty clever guys. We find out ways to make things work, even when like it might seem that there is no real solution to the problem. So they thought that instead of making these generic back and front contacts, why not do something like this? Like, so does any of you know? So here's a question from my side. So does any of you know how an optical fiber works? Anyone? How an optical fiber works, or the basic principle of an optical fiber communication? Okay, so
You guys sure I talked about this in geometry.
really?
You put lights on one end and get lights on the other end.
Okay, but how?
Doesn't it maintain total
Reflection.
internal reflection?
Yeah.
Yeah. So what it does, it traps the light inside of your optical fiber by this principle of total internal reflection, so that light cannot escape in your structure. So this part of like using a very similar technique here, where they actually first try to first go with very basic grating structures at the top surface, so as to trap light more in your solar cell. When they saw that, well, we can really like increase the amount of time that light stays trapped inside my solar cell, I can actually go for much more advanced strategies of, instead of going for simple grading structures, I could go for optimized grading structures. So what's one problem with simple base gradings? Does anyone recall? So what's the problem with a simple Blaze grading structure? So the question is, instead of going for this, why did they optimize the structure from a Blaze grading structure? I didn't go over this? Okay. Okay, so since it was not told, I'll answer this. So if you look at a simple Blaze rating structure, a Blaze rating structure is designed to operate at a single wavelength. It is optimized to operate or blaze the incident wavelength, a single wavelength. But when we are talking about solar spectrum, we are talking about a broadband range from 250 to 2500. So we are talking about a wavelength range of close to 2250. So what they try to do is, right now they try to take this broadband light and try to uh, make all these wavelengths stay inside your solar cell. And when this approach seemed successful, they optimized both the back as well as the front contact to increase this uh, time even more. So this is a schematic of the structure that they came up with. As you can see that they came up with the optimized structures at both front as well as, I don't think if it's clear, pretty much clear here, as well as the back contacts. And from 14.7% they increased the efficiency to 25.2%. So you have an efficiency increase with these kind of optimized structures by greater than 10%. Now this what's okay. So what this happened is that so I guess so this with a simple structure like this, with reverse engineering, with optimized clever engineering, they were able to increase the efficiency of their solar cells by 10%. So this is one of the earliest demonstrations of how optimized structures, careful parametric geometrization of your solar cell itself can give you more efficient structures in itself. So I think this was the backside contact. Okay. So once we come, so the first generation, fine, material silicon. What we do, we optimize the structures, increase. What next? Again, the material. So by the time they were playing around with all these geometrical characteristics, we have progressed in the material science perspective. That is in the form of thin film technologies. So traditionally what people used were bulk silicon crystals. So what these material guys, they were trying to outsmart their electrical counterparts, saying, haha, like you can do geometry parameterization, but we can come with clever approaches in materials in itself. So what they said was, well, silicon, as you know, is indirect band gap semiconductor. So what this typically means here, that the top of your valence band as well as the bottom of your conduction band are not really aligned. So you need typically a greater amount of energy so as to transport the electron from the valence to the conduction band for electrical current generation, in essence to a direct band gap semiconductor. Now if we take these silicon structures and make them pretty thin. Now again, I'm not going into why this principle works, since this probably is outside the outside the course objectives, but they said like if you can use a thin film which is traditionally 100x thinner than what was traditionally used at, of 200 to 300 microns, you can actually treat this as direct band gap semiconductors, and right now you can actually harness silicon, the same material itself, which for an indirect band gap and a higher energy requirement, into a direct band gap with a lower energy requirement. And this increased even without doing any parametric geometrization, without doing anything, from 25% to like 22% for other materials like cattail and all. So what they did was they generalized this not only for silicon but also for other materials like cattail and all this stuff. So even without doing any such thing from a material perspective itself, they increased the efficiency by 10%. So speaking of other materials, which as he was talking about mass production, they said like, well, silicon might be a bit difficult to produce. What about cattail? They look pretty cheap to produce. So as a competition to silicon, what we have is two solar farms, as we prefer to call it, in US itself. I guess these are in US, right? So one is at the huh? Okay, forgot. So one is the so let's I guess it's US. So one is in the Topaz Solar Farm, where currently they are operating these cattle panels for 550 milliwatts, and the other is the Aqua Caliente, which typically at 290 megawatts, still pretty lower than China, but still uh, where you have this first solar cattle panels.
Yeah, they're both in US.
They're both in
California
US.
and Arizona.
Okay, California and Arizona. So yeah, so they have this new setups coming up with cattle, which has greater than 20% efficiency without any geometric parametric optimization in itself from just the material perspective. Now, apart from these thin film technologies, apart from cattle and silicon, we also have these organic electronic materials or the organic molecules, which again can be used to make these kind of solar cells. So right now, so in the second generation, people mainly concentrated on the material perspective of these kind of solar cells. So the advantages of these kind of organic semiconductors is what you have, like instead of having a valence and a conduction band, what you have in these kind of organic molecules are orbitals. So instead of having a material where your dielectric constant or like or high refractive index materials, you can actually have these organic molecules, and what you right now you have a Coulombic binding or an exciton pair. So an exciton is nothing but a hole and electron pair to generate electric currents with very low power requirement in comparison to conventional semiconductor materials. Now this was harnessed later on to much more advanced materials or complicated materials, perovskites. So perovskites is pretty recent, like as you can see, the revolution or the discovery, or what should I say, the study of perovskites started in the year 2010. Uh, right now even to the year of 2020, where you can see that various universities around the world have started uh, making these perovskite structures and increasing the efficiency from 4% right up to 20%. Now thinking of perovskites, so perovskites are nothing but an amalgamation of a metal. Wait, this would be easier to understand. So it's an organometal halide perovskite. So it basically has a halogen group in itself, it has an organic material in itself, and it also has a metal. So thinking of this structure here, so the metal here that you have is lead molecules, the halogen group is iodide, as well as the organic molecules that you have here is basically a CH3NH3 plus molecule. So these are a bit complicated structures to understand, but people have really shown that over the years this can be manufactured with certain ease, such that they can be used in the manufacture of solar cells. So once the biggest what should I say, the biggest achievement for these kind of thin films, organo halide perovskites, as well as these organic molecules have led to the formation of really thin film solar cells. As you can see that these ultra thin perovskites have really shown that the power per weight that you can achieve across the solar cell is again huge, as this can be used to make all these kind of lightweight aircrafts and all this with really low cost. I mean, low cost is probably still a pretty debatable word, but still. So, so the second generation, they were like, okay, the material scientists gave us a good fight. Again, let's go back. Let's go back to doing geometrical parameterization. So now, so first thing is they said we have the materials. Now let's do one thing. Let's make a solar cell. Let's make a multi-junction solar cell. So as you have seen, these different kinds of materials have different signatures in different absorption bands. So what they said was, they said let's take each of these materials as we have in itself and sandwich them one on top of the other, such that each forms a junction of its own and each can optimize at its own specific wavelength. So what they said is, what they shown that with the number of junctions, with the increase in the number of junctions, you can actually increase the efficiency of your solar cell by a huge amount. So this was shown pretty late from, I guess, the Enel folks, that you can actually make these kind of multi-junction solar cells without even having to worry about materials. Or let's say you have a thin film material. So what you have specific or many layers of this thin film material, it's still pretty thin. You can actually make a solar cell which is efficient up to 72%. So what they shown is that if you employ different materials which have different good performance in various bands, you can actually typically mimic the plot that I showed you of a box across this entire wavelength of regime. So this is typically the structure of a multi-junction, or what we call a tandem solar cell. We have different materials, different compound semiconductor materials that you can see that typically has a good performance.
Yeah, Dr. Menon also discussed about
Yes, so I guess, yeah. So Dr. Menon also discussed about this, and this again, like, typically is a bit difficult to manufacture, but again, so like the final thing that I wanted to discuss is other advanced engineering techniques apart from this multi-junction and all this, which really can come, is a radial junction solar cell, which said, like, again, parametric optimization. So what if instead of all these single materials, you make these pillars, these rods of these wire arrays of materials which can actually help in capturing the solar light and trapping it within the solar cell in itself. Also, okay, so there's only one slide for this. So this is I'll not probably
Just
go
the,
into much
the increase in
details.
surface area.
Yeah, so it's like so with the increasing surface area across these kind of structures, you can again do parametric or geometric optimization to trap light at the expense of not having to go for various other different materials and make these kind of structures. So this is just a simple slide. I'll probably not go much into this. So like to summarize everything, what we have seen is the first thing is solar cells or photovoltaic cells have exponentially grown over 2 decades and oh, I never knew of this. So there's the Swanson's law in photovoltaics, which is very equivalent to the Moore's law. And again, so solar cells requires absorption, separation, and collection in itself. But like, if you ask me, the basic challenge is to how to make these kind of solar cells from both a material perspective as well as a geometrical parameterization perspective. How you can actually create a mix and match play of these two techniques to make these kind of solar cells. And again, so there, as I was saying, from a material perspective, there are a lot of viable technologies, some of which has been shown here, and honestly, a lot of it has not been shown here. So if you go to Google and type all these alternate type of technologies which have been shown, you could see that one material is definitely not the answer. Again, pretty debatable because tomorrow material science can come up with a wonder material which can cover everything. So you never know. And high efficiency takes savvy engineering. So yeah, I mean, again, so without having to go much more into the material perspective, you can do clever tricks of how you can make more highly efficient solar junction or solar cells. So with this, I guess this is the end of this lecture. Any questions that you have?
Okay, so if there's no any questions, let's thank Sharon for
I think we are on time.
thanks for
This is the recording.